Hello students, welcome back to KCET Masterstroke series, and in today's class we are doing the one shot of the chapter Electrochemistry. Okay, so I'll be giving you all the important formulas, concepts from this chapter that you need to revise to crack this chapter for KCET examination. Okay, so let's get started here. So I have divided this chapter into three parts. Okay, so in the first part we are going to discuss about galvanic cell and Nernst equation. Okay, I'll be focusing mostly on the KCET based concepts. Okay, there are a lot of theories in this chapter, but our target will be the KCET theory. Okay, next we have electrolytic cell and electrolysis, conductance of electrolytic solutions, then we will discuss about batteries, fuel cells and corrosion. Okay, so let's get started here. Weightage, consistently you can see 3 questions have been asked, but again I guess that this year the number of questions will definitely be more because the syllabus has reduced, so you can easily expect 4 to 5 questions from this chapter. Okay, next let's discuss the first part, that is galvanic cell. So what all things I'll be talking about galvanic cell: the basic construction and working, cell notation, measurement of electrode potential and calculation of cell EMF. So in galvanic cell we'll be talking about construction and working, cell notation, measurement of electrode potential and calculation of cell EMF. Okay, yes. Then in Nernst equation we will see Nernst equation, how can we use to calculate the electrode potential for the cell and for the electrodes, what is equilibrium constant, how is it related to Nernst equation, and Gibbs free energy. Okay, so mostly electrochemistry is formula based chapter. We have to focus more on the formulas and less on theory. So first, basically what is a galvanic cell? A galvanic cell is something which converts the chemical energy into electrical energy. Okay, and it is a spontaneous process. Delta G for this one, because it is spontaneous process, delta G is negative. Example is your Daniell cell. Okay, so the main thing that you have to focus here is conversion of chemical energy to electrical energy. So now what about the working here? Yes, so if I just explain you the working, so please understand it carefully. Here we have Daniell cell we have taken, where I have taken zinc rod as anode and copper rod as cathode. Okay, so in this what happens, the zinc from the solution, yes, so the zinc from the solution comes out, okay, as Zn2 plus. Yes, so zinc from the solution comes out as Zn2 plus, okay, releasing electrons on the rod. Okay, now these electrons come from the wire, okay, come from the wire and get accumulated here. Okay, now what happens in this solution, we have copper 2 plus solution. Okay, now copper 2 plus solution takes these electrons and get deposited on the electrode. So now if I want to show you the reaction here, so it is like this. Just a minute. Yes, yes, so what happens exactly at anode? Okay, so if you see at anode, the reaction that takes place is zinc gets converted to Zn2 plus 2 electrons. Okay, and at cathode, okay, what we can find is Cu2 plus 2 electrons gets converted to copper. Okay, so now if I add these two reactions, this is my overall cell reaction. Clear? So at anode what you can see, there is loss of electrons, at cathode there is gain of electrons. Okay, and in this what happens, the anode is negatively charged and the cathode is positively charged. Clear? Now this is something called as your Daniell cell, or how the cell is working. So you can see when the chemical reactions are happening, the electrons are moving, right? These 2 electrons that have been released here, right? These electrons are moving. So due to this flow of electrons, the current is generated which moves in the opposite direction. Clear? Now my thing is, the next thing that we are going to discuss is about the electrode potential. What is electrode potential? Now you see in this rod what happens, Zn2 plus comes out, right? I can write Zn2 plus here and electrons here. So this electrode is negatively charged, whereas the solution is having more positive Zn2 plus ions, and that is a positively charged. So you can see the interface between these electrons and the Zn2 plus ions. Okay, there is a charge difference between that two, and because of this charge difference, a potential is developed between these two. Here some potential is developed. That potential is called as electrode potential. Let us see here. Okay, a potential difference develops between the electrode and the electrolyte, which is called as electrode potential. When the concentration of all the species involved in a half cell is unity, then the electrode potential is known as standard electrode potential. So if this solution is 1 molar, okay, if the concentration of the electrolyte is 1 molar, then we call it as standard electrode potential. Okay, after that, standard reduction potentials are now called as standard electrode potential. Now see, here the potential that is developed between electrode and zinc, that this is called oxidation potential. Here the potential that is developed between the rod and the electrolyte is your reduction potential. But for convention, for according to IUPAC, when a reduction potential is taken as electrode potential. Okay, so whenever we talk about electrode potential, we have to talk it in terms of reduction potential, so that a common term can be used for all the electrode potentials. Okay, so whether it undergoes oxidation or reduction, the potential is always expressed in terms of reduction potential. Okay. Next we have, according to the convention, a half cell called a standard hydrogen electrode is represented by, this is the hydrogen electrode. Okay, now what is the role of this hydrogen electrode? See, to measure the electrode potential. Okay, so here I have, see, generally what will happen, let me explain it in a very simple way. So you have taken, yes, so we have taken 2 chambers. Okay, so what exactly is there? See, suppose here there is a voltmeter. Now there is this side there is oxidation potential and this side there is reduction potential, right? Now some value is here, some value is here. The difference between these 2 potentials is something which is measured by the voltmeter. Okay, the difference between the 2 potentials is measured by the voltmeter. Now suppose, for example, I take here suppose the value is 0.76 and minus 0.76, and suppose the value is 0.34. So the difference between these 2 is measured here. Clear? Now what happens, suppose I want to measure the electrode, so I need to know this value and I need to know this value, right? Then only I can subtract this. So now what happens, to take as a reference, okay, one second, yes, to take as a reference one of the electrode is considered as a hydrogen electrode. Okay, hydrogen electrode is taken on one side. Suppose I want to measure the reduction potential of zinc. Okay, so I will take zinc on one side and hydrogen electrode on the other side. So now this hydrogen electrode potential is considered to be 0. Okay, so now suppose this A and this is B. Okay, so I want to find the value of this one. So if suppose this value comes out to be C, now I can write that A minus B is equal to C. Okay, sorry, A minus B is equal to C. Okay, now what happens, that means and suppose one of them is already 0, that means C is this is 0 and 0 minus B is equal to C. So I can say that C is equal to minus B, means the reduction potential of this side is nothing but the minus B value. Okay, so we can easily calculate the reduction potential of all the electrodes by taking one reference electrode, and that reference electrode is your hydrogen electrode. Okay, so the electrode potential of the whatever, in the hydrogen also there will be some potential difference, right? But it is taken as a reference and it is assumed to be 0. So if this is 0, then whatever difference comes, that difference will be nothing but the electrode potential of this one, right? So that is how we can use hydrogen potential or hydrogen electrode as a reference electrode. Okay, and it is represented like this, and it is potential is assigned to be a 0 potential. Okay, next coming to measurement of electrode potential, as we have seen, so you have taken zinc on one side and hydrogen electrode on other side. Whatever values comes here, because this is 0, that value will be given to zinc. Okay, so you can see here it is measured with the help of a reference electrode known as the standard hydrogen electrode. Okay, the standard electrode potential of an electrode can be measured by pairing it with SHE and measuring the cell potential of the resulting galvanic cell. So whatever value comes here, I have taken hydrogen electrode, whichever electrode potential I want to measure, I will keep it on this side. Whatever values comes here, that value will be the reduction potential of this particular electrode. Okay, because this is assumed to be 0. The potential difference between the 2 electrodes of a galvanic cell is called cell potential and is measured in terms of volt. The cell potential is the difference between the electrode potentials of the cathode and the anode. Okay, so E, that is the cell potential, can be calculated by E cathode minus E anode. Okay, so E cathode minus E anode, and both of this potential values should be in the form of reduction potentials. Okay, let us see now. Okay, a question. Okay, let's revise what else we have studied till now. Yes. Okay, so in a galvanic cell, what happens? The chemical energy is converted to electrical energy. It is a spontaneous process, so delta G will be negative. Okay, then at anode, oxidation will take place. At cathode, reduction will take place. Anode charge will be negative charge, cathode will be positive charge. Cell notation, how to write, we have understood. Or let me tell you once again how to mention the cell potential. So I have suppose this rod, right? Okay, so you have to remember that you have to start from the left hand side. Okay, so what I have taken here, suppose zinc sulfate. Okay, this is zinc rod, this is copper rod, and this is copper sulfate. So you have to start from here. Okay, so here what is happening, we have start from here. This is my zinc rod. Okay, and I have salt bridge here. So you have to start with zinc rod. Okay, then zinc rod is in contact with Zn2 plus. Okay, now after that Zn2 plus is in contact with salt bridge. Then here we have, this is in the solution Cu2 plus, and then we have copper rod. Okay, so this is your cell notation. Clear? Next, electrode potential. What is electrode potential? Electrode potential is the difference between this potential, means what? The difference between the charge or the potential developed between the electrode and the electrolyte. That is called as your electrode potential. Next, what is cell EMF? The difference between the anode potential and cathode potential is called as your cell EMF. Okay, so these are the terms that we have discussed now, and I hope it is clear to everyone. So let's do a small question here. So copper plus 2 Ag plus gives you Cu2 plus 2 Ag. Write the half cell reaction. So we can easily write, so I can see copper to copper 2 plus is oxidation, Ag plus to Ag is reduction. So oxidation will always take place at anode. So let me write the reaction for anode. It is Cu2 plus, right? So I will get 2 plus 2 electrons. Then Ag plus to Ag. So I have at cathode. Okay, so 2 Ag plus 2 electrons gives 2 Ag. Right? Now to make the number of electrons same, it is already same, right? So what I can do, you have to write the half cell reaction. So that is done. A part is done. Next, B is cell notation. So for cell notation, what we have to do? So first you have to find out the oxidation part. So if I just imagine, okay, cell notation, or let me just write down the full cell reaction. It is Cu plus 2 Ag plus gives me Cu2 plus 2 Ag. Okay, so now you know that you have to start from the left hand side, and on the left hand side we have oxidation, right? So copper is undergoing oxidation, so it has to be Cu to Cu2 plus. Okay, then after that salt bridge will come. Right hand side there will be reduction. So reduction is from what? Ag plus to Ag. So it is, okay, here I want to tell you a mnemonic that you should always remember. It is lone. Okay, so what is lone? Lone stands for left, O stands for oxidation. Oxidation takes place on anode, and the anode charge is negative. Okay, so please remember this one. This will solve all of your problems. Next, expression to calculate the EMF of the cell. So if I want to calculate the EMF of the cell, E of the cell will be equal to E naught of cathode. This is anode, this is cathode, right? So E naught of cathode, okay, minus E naught of anode. Okay, so now let's move forward here. An electrochemical cell generally consists of a cathode and an anode. Choose the correct statement with respect to cathode. Oxidation occurs at the cathode. Electrons move into the cathode, usually denoted by a negative sign, is usually made up to an insulating material. You have to tell the correct statement about cathode. Cathode, always reduction will take place. So oxidation occurs at cathode is wrong. usually denoted by a negative sign? No, just now we have seen in Daniel's cell that the cathode is represented by a positive sign, right? So that is why this is also wrong. This is also wrong. It is usually made of insulating material. No, copper itself is a conducting material, right? Now electrons move into the cathode. So if you have seen here, what happens in case of zinc and copper, what we observed, zinc came out as Zn2 plus, right? It released the electrons here. Now these electrons moved and entered to this surface, right? So cathode is something where the electrons are entering. So that is why here B is the correct answer. Okay. Next, we have the definition of, let's start with the Nernst equation, the second part. So we have understood what is a galvanic cell. Okay. So now what is Nernst equation? Why it is required? So to calculate the cell EMF under non-standard conditions. Now see, the formula to calculate the cell EMF is what? We have this formula, right? E naught of cathode minus E naught of anode. Here this naught I am providing, right? This naught means that the electrolyte that we have taken must be at 1 molar concentration. Then only we can use this formula to calculate the electrode potential or the cell EMF. But in case there is no concentration is not maintained at 1 molar, then to calculate the cell potential, okay, that cell potential, the difference between the oxidation and the reduction potential, to calculate the cell potential we use Nernst equation. I hope this is clear. What is Nernst equation? Just understand, we have a cell. If it is 1 molar electrolyte is there, then simply we know the electrode potential of zinc, we know the electrode potential of copper, that we have calculated using the hydrogen electrode. There is a table where all the electrode potentials have been mentioned. Just we will subtract cathode minus anode, we will get the answer. But what if the solutions are, the electrolytes are not maintained at 1 molar? In that case, what we have to do is we have to do something called as Nernst equation. Okay, so Nernst equation helps us to calculate the cell EMF under non-standard conditions. Non-standard conditions means when the electrolyte concentration is not 1 molar. Okay, so now let us see. Nernst equation we are going to study for two things. For electrode means you have taken hydrogen on one side and you have taken copper electrode one side, but the electrolyte is not 1 molar. So when you want to calculate for any pure electrode, okay, at that time we will see how to find the Nernst equation. And if you want to find for the cell, two different metals you have taken and the concentration is not maintained at 1 molar, how to find the electrode potential, okay, or cell EMF. So for electrode, okay, so suppose we have any electrode where Mn plus is undergoing or taking n electrons to get reduced to M solid. So what will be the reduction potential here? E naught minus RT by NF log, this side log 1 by this one, okay, product minus reactant. So on the product side there is no ion, so it has to be 1, this has to be taken as 1 divided by the concentration of Mn plus. Since it is not 1 molar, so there will be a different concentration, we have to consider that, okay. So if you just modify it, okay, so we will get here, this one value will become 1 because it is a pure solid, okay. Now if I want to further modify it, it is like this, Emn plus to the power m, okay, is equal to E naught Mn plus m, okay, minus this one. If I convert into 2.303, I convert it to log and I substitute all the values, I'll get 0.059 by n, 0.059 by n log of 1 by m n plus, okay. So this is fine, clear. So now in this way we can find the electrode potential of a electrode in non-standard conditions, okay. Now here we have for cell, Ni plus 2 Ag plus gives Ni2 plus 2 Ag. Now here also if I want to calculate, I have for anode, okay, anode means nickel is getting converted to Ni2 plus, oh 1 second, okay, just a minute, let me write down this one for you. So first of all, if I want to write the reaction, so E of the cell will be equal to E naught of the cell. E naught of the cell we can easily calculate by, so you can see nickel is undergoing oxidation and this one is undergoing reduction. If this is reduction means this is cathode and this is oxidation means this is anode, right? So it is cathode minus anode, right? So we can easily subtract silver minus nickel and we will get this E naught value. But the term we are not finding E naught value because these are under non-standard conditions. So E naught of the cell minus RT by NF log Ni2 plus by Ag plus square. So you have to take products ions divided by reactant ions. So reactant ions are there and that has to be taken to the power of 2. Okay. Now here you can modify it. E of the cell is equal to E naught of the cell minus 0.059 by N log nickel 2 plus by silver plus square. Clear? Okay, next we have this question. The electrode potential of copper electrode dipped in 0.025 m copper sulfate solution at 298 Kelvin is. So you can see here the concentration is not 1 molar, so it is a non-standard condition. So we have to use Nernst equation for pure electrode. Standard reduction potential of copper is already given to us. So what is the formula? Let us substitute. E of the copper, okay, is equal to E naught of copper minus 0.06 by 2. For easy calculation, we'll take 0.06 by 2 log of, okay. So what is the ion here? We have Cu2 plus 2 electron gives copper, right? So 1 by Cu2 plus. Clear? So now what will happen here? If I just want to do this one, so E naught value is 0.34, okay, minus 0.03 log of 1 by Cu2 plus is 0.025. Okay, so now if I solve this, okay, so if I solve this, you can first of all think that the answer has to be less than 0.34, okay. So we can easily eliminate these two options, okay, and it won't decrease too much, okay. There is a slight decrease in the electrode potential, so this is very much less than 0.34 volt. So this is also not the correct answer. You can easily find the answer is 0.293, okay. If you solve it you will get, but you can guess in this way as well. Now if I move to the second question, here we have already been given, it is a cell electrode potential or the cell EMF of copper and silver electrodes are taken. E naught values are also given. E of the cell will be, we don't have to calculate fully, you just have to find the expression, okay. So let us start here first. E of the cell, so if I write this reaction, copper is undergoing what? Oxidation. So it will become Cu2 plus 2 electron. This is at anode. At cathode what will happen? Ag plus Ag. Okay, so it is 2. Now let me add this reaction. It will become Cu plus 2Ag plus becomes Cu2 plus 2Ag. Right? Now what we'll be doing? Now we can just write the equation. E of the cell, okay, is equal to E naught of the cell, okay, minus 0.059 by N log of product ions. Product is copper 2 plus, okay, reactant is silver 2 plus, silver plus. Now here 2 is there, so this 2 must be taken as a coefficient, power, okay. This coefficient must be considered as a power. So now E naught is already given to you 0.46. So if I solve this, I'll get, so 0.46 minus 0.059. What is the value of N? Number of electrons we have used is 2. 2 log of, what is copper 2 plus concentration? Copper 2 plus is 10 to the power of minus 3 and Ag plus is 10 to the power of minus 5 into 2. So it is 10 to the power of minus 10. So it goes up, okay, it will become 10 to the power of 7, okay. So you can see here I have 10 to the power of 7, 0.46 and 10 to the power of 7. So I can easily eliminate these two options. Now coming to this sign, okay. So you can see here this is coming negative, right. So this is also incorrect. Option number 2 is the correct answer here, okay. Let's next go to the equilibrium constant part, the relation between E naught of the cell, okay. So when the cell is at equilibrium, okay, E of the cell E of the cell is considered to be 0. Okay, so E of the cell is 0, that means I can write E naught of the cell will be equal to 0.059 n by log k. Sorry, 0.059 by n log k. See, this was the Nernst equation, right? E of the cell is equal to 0.059 n log k. Now, if this E of the cell is equal to 0, then what I'll get? E naught is equal to log k, right? So, this one what we can get here, E naught of the cell will be 0.059 by n log k. Clear? Now, we'll go to this one, Gibbs free energy, the relation between Gibbs free energy and E naught of the cell, that is delta G is equal to minus NF E naught of the cell, and one more equation we have, delta G is equal to minus 2.303 RT log K. Okay, so these are the two formulas related to Gibbs free energy. We can do a small question here. H2 plus 2 AgCl gives 2 Ag plus 2 HCl. E naught of the cell is given to you. You have to find the equilibrium constant. So we have this relation, right? Sorry, yes, I have this relation. E naught of the cell is equal to 0.059 by n log of k. Okay, what is the value of E naught of the cell? 0.22, and here n value you can see it is 2 value, 2 n is 2, so 0.06 I will make it for easy calculation, log of k. Okay, so it is 0.03, so 0.22 by 0.03 you will get 7 point something, 7 is equal to log of k. So k is nothing but 10 to the power of 7, so you can find there is some values but we'll get power of 7. So option number A will be the correct answer. How easily you can solve it. Okay. Next, which of the following is correct, is incorrect in a galvanic cell? Okay. Oxidation occurs at anode. This is correct for all the cells, whether it is galvanic or not. Reduction occurs at cathode. That is also correct. You have to find the incorrect statement. The electrode at which the electrons are gained is called cathode. Yes, this also I explained. On the cathode side, the electrons will be gained. The electrode at which the electrons are lost is called cathode. No, from where the electrons are lost, that is called as anode. So the correct answer for this question will be option number D. Let's move forward. Here this is important PYQ question of 2023. Consider the following 4 electrodes. Okay, the reduction E naught value is given to you. The reduction potential in volts of the electrodes are in the order. So you have to just calculate the reduction potential. So you do not have to do full calculation. I'll tell you how to do. See, Ag plus will undergo the reaction like this, right? Okay. So what will be my equation? E of the cell is equal to E naught minus 0.059 by n, 1 electron only, by 1 log of 1 by Ag plus concentration. Okay. Now here E naught value is 0.8. So this also I can further make it as 0.8. Okay. Minus 0.051 log Ag plus. Now what we have to calculate? This number, right? This is a number which has to be subtracted. So if this number is very big, then you are subtracting a big number from 0.8 and the E value will decrease. If this value, this total value is a small value, then you are subtracting a small number from this one and the total value will be a bigger one. So we have to just calculate this part for all of them. Okay. So let us do for the first one, that is your A given. Okay. So I will get E of the cell is equal to 0.8 minus 0.059, okay, log of 1 by Ag plus concentration is 10 to the power of minus 3, right? Right. So this will go up, it will become 10 to the power of 3, sorry, 10 to the power of 3. So it will become into 3. Right, 10, it is log of 10 to the power of 3, 3 log 10, so into 3 I got here for option number A. For option number B it will be, I can just write it quickly, minus 0.059 into B it will be log 1 by 10 to the power of minus 1, right, it will go up log 10, so it is into 1. Next here E will be equal to 0.8 minus 0.059 log of 1 by 10 to the power of minus 2. So it will go up, it will become 10 to the power of 2. So 2 log 10. So it is into 2, right? So here it is into 2. Then here E is equal to 0.8 minus 0.059 into here I can easily make it 1, 2, 1, 2. Both of them are same. Just a minute. Okay, this one is actually, just a minute. Okay, so this one is actually 0.0001. Okay, so this is 10 to the power of 4. A small correction here. This is 4 and this is 3. Okay, now you see we are subtracting this one. The smallest number is here, right? That means we are subtracting a small number from the 0.8. That means this one will be the highest value. So B is highest only in one option. So we can eliminate this one. After that it is C. After that it is D, and after that it is E. Okay, so option number A is the correct answer for this question. Next, we'll move to the part 2 of electrochemistry, where we will be discussing about first electrolytic cell. Okay, in electrolytic cell we'll talk about Faraday's law, products of electrolysis, and the difference between a galvanic cell and a electrolytic cell, so that you can have a clear understanding of what are the two cells. Okay, after that in electrolytic conductance we will be talking a lot of things here. Okay, so we'll be discussing about the factors affecting the electrolytic conductance, important terms, their definitions and symbols, formulas also we will discuss, variation of molar conductivity with the dilution, then we'll talk about limiting molar conductivity, Kohlrausch's law and its application. So please stay tuned, a lot of formulas are coming in now. Okay. So starting with electrolytic cell, so just like we have discussed about galvanic cell, so what basically is electrolytic cell? It is a cell where the electrical energy is converted to chemical energy, means you provide some electricity, due to this electricity there is a chemical reaction taking place. Okay, this is a non-spontaneous process, obviously, because we are providing the energy, right? We are providing the electrical energy because of which the chemical reaction is taking place. So it is a non-spontaneous process. If non-spontaneous, delta G has to be positive, and in this case anode is positive and cathode is negative. Okay, if you remember in galvanic cell the anode was negative and cathode was positive, but here also in this cell also, in anode there is always oxidation and at cathode there is always reduction. So this definition is standard definition for anode and cathode. Whenever you are asked a question what is an anode, your answer should not be it is a negatively charged or positively charged electrode. No, it is an electrode on which oxidation takes place. This can be negative for galvanic cell, it can be positive for electrolytic cell. So the negative positive doesn't determine the anode, it is the reaction that takes place, the oxidation reaction which takes place on whichever electrode, that will behave as the anode. Okay, example, it is used for obtaining pure metals. Okay, we are doing a lot of electro refining process, in this we use this electrolytic cell. Now coming to the next topic, that is Faraday's law. So we have two laws in Faraday's, that is Faraday's first law and Faraday's second law. So what does Faraday's first law tells us? See, whenever I told you, whenever there is a when we provide some electricity, there is some chemical reaction is taking place, right? When this chemical reaction will take place, product will also be obtained. So the Faraday's law tells you, if you provide a certain amount of quantity, how much product or how much chemical reaction will take place. Okay, so you can see here the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed. How much current, how much electricity you are giving, based on that the chemical reaction will take place, based on that the product will be formed. So we can calculate how much mass of the product has been formed based on how much quantity of electricity is provided. So you can see here we have this formula, M is equal to ZIT. So what is M here? M is the mass of substance deposited at cathode. Okay, this is your M value. Now what is Z? Z is electrochemical equivalent. Okay, now Z is electrochemical equivalent. How do we calculate Z? Z is molar mass divided by N into 96500. Molar mass of what? molar mass of the substance deposited. Okay, N is the number of electrons required for the reduction reaction. Okay, next we have I is current and T is time in seconds. Clear? So we will get ZIT in this one. So here the mass deposited is directly proportional to the I into T is what? Current, means I into T is charge. So the total amount of charge is passed, to that the mass deposited is proportional. Next, coming to the second, Faraday's second law. So the amount of different substances liberated by the same quantity of electricity passing through an electrolytic solution are proportional to their chemical equivalent weight. So now when the two cells are in series, okay, so the mass deposited on one cathode and the mass deposited on the other cathode, what will be, how can we find that? So we have a formula for that. M1 by M2 is equal to E1 by E2, where M1 is the mass deposited on the first cathode, M2 is the mass deposited on the second cathode. E1 is the equivalent weight deposited on the first cathode, E2 is the equivalent weight of deposited on the second cathode. Okay, so now what I can have is how to calculate this E1, E2. So E1 or equivalent weight is equal to mass, okay, molar mass divided by N factor, where N factor is the number of electrons that have been included. Okay, number of electrons that is involved. Molar mass by N factor is your equivalent weight. Molar mass by N factor is the equivalent weight of this one. Okay. Next, if we move towards solving the questions, how many coulombs of electricity are required for the reduction of 1 mole of MnO4 minus to Mn2 plus? So if I want to reduce this one, okay, this chemical reaction has to take place, then how much quantity of electricity you have to provide? That is the question. Now if you see MnO4 minus Mn is in +7 oxidation state, okay, and here we have Mn2 plus, okay, so here we have 5 electrons. So now 5 electrons means 5 moles of electrons. Okay, so 5 moles of electrons, 1 mole of electron is 96500 coulombs. So 5 moles of electrons means 5 into 96500. Okay, so we have here 5 5s are 25, 5 6 are 30, 32, 48. So almost this one, option number C here. Okay. Let's move to next question. A certain quantity of electricity is passed through an aqueous solution of AgNO3 and cupric salt solution connected in series. The amount of silver deposited is 1.08 gram. The mass or the amount of copper deposited will be. So if I have copper, mass deposited of copper by mass deposited of silver, okay, is equal to the equivalent weight of copper by equivalent weight of silver. Okay, so now if I want to calculate this one, we have mass of copper deposited. So here mass of copper deposited is taken to be, okay, sorry, silver deposited is 1.08. So I just have to substitute 1.08. Now equivalent weight of copper will be 63.5 divided by 2, because copper is getting reduced in this form, right? Cu2 plus 2 electrons gives you copper, right? So 2 electrons are taken here. So I will get 63.54 divided by 2. And here we have Ag, silver equivalent weight is how much? 1.08. So molar mass is 108 and the electrons that is involved is 1. Okay, so it is 108, sorry, into 108 by 1. Okay, so now if I solve this, what will I get? Mass of copper deposited will be 63.54 divided by 2 into 108 by 108. Okay, so we have this one. 1 second, let me just check. Okay, so we have to solve this one now, right? So I will get 3 point something here, right? So that is 0.31 I will be getting, 0.31, option number B is the correct answer. Okay, now coming to products of electrolysis. So when a electrolytic solution is undergoing electrolysis, when you are dividing that solution using electricity, different products will be formed at anode and at cathode, right? So let us see that. So if you have taken molten NaCl, okay, so what you have Na plus and you have Cl minus. Na plus will move towards cathode and Cl minus will move towards anode. So what happens at cathode? We have reduction, so sodium metal will be produced. At anode, Cl minus is there, okay, chlorine gas will be produced. Next we have, so what is the reaction that is taking place at cathode? Na plus plus electron gives you Na, okay, and Cl minus plus half Cl2 plus electron, that is your anode reaction. Now if you take aqueous NaCl, so we have H plus also and OH minus also. So out of H plus and Na plus, H plus has more tendency to undergo reduction. So what will happen? Hydrogen gas will be produced and chlorine gas will be produced. Similarly, you can see for this one, dilute H2SO4, H2 gas and O2 gas will be produced. Concentrated H2SO4, H2 gas and S2OH 2 minus will be produced. Here you can see in electroplating, the metal to be electroplated is. So here the pure metal will be deposited on the metal which is electroplated. So deposition will take place on cathode. So that has to be taken as a cathode here. During electrolysis of concentrated aqueous NaCl, the gas produced at cathode. So at cathode we have which gas? So you have here H plus gas will be produced at cathode, right? Because it is aqueous solution of NaCl. Okay, now let us see a difference between galvanic cell and electrolytic cell. Very, very important. You should have a clear understanding. So in a galvanic cell, produces electricity using chemical reaction. Okay, chemical reaction is converted to electrical energy, and here it requires electricity to create or to drive an chemical reaction, or electrical energy is converted to chemical energy. So yes, that is the same point. This reaction is spontaneous and this is non-spontaneous. Okay, here cathode is positive, anode is negative, and here anode is positive and cathode is negative. Ions are discharged at cathode while on anode they are consumed. So in galvanic cell, what happens? From the anode, the negative electrons comes out, and at the cathode they are collected. Okay, here what happens? Ions are discharged at both the electrodes. Now electrons move from anode to cathode, and here electrons move from cathode to anode. Half cells are set up in different containers, half cells are set up in the same container. Electricity produced as a result of chemical reaction is measured by coulometer. The EMF of the voltage provided to the cell is measured by the potentiometer. Okay, so what voltage you are giving to that particular cell, that is measured by potentiometer, and here due to the chemical reaction what cell EMF has been produced, that is measured by coulometer. The galvanic cell has its applications in batteries. Electrolytic cells are used in electroplating. Okay. Now we have something very, very important, the conductance of electrolytic solutions. So as you know, a metallic conductor is there, it can conduct electricity, right? Similarly, electrolytes are also having the ability to conduct electricity. Okay, electrolytes. So now for electrolytes we have these factors which affect the electrolytic conductance, that is your nature of the electrolyte added, which type of electrolyte you have taken, size of the ions produced and their solvation, okay, the size of the ions that is being produced, nature of the solvent, concentration of the electrolyte, temperature, it increases with the increase of the temperature. Okay, so we have nature of the so this can be a very important question, like 4 options will be given, which is a factor that affects, which is not affecting, so you should be knowing. The first one, nature of the electrolyte, that means strong and weak electrolyte. Second one, size of the ions, bigger ions means less conductivity, small ions means more conductivity. Nature of the solvent, if the solvent is very viscous, okay, the ions cannot flow. Okay, so that is why conductivity will decrease. Next, concentration of the electrolyte, more ions, more conductivity. Next, temperature, it increases with the increase in temperature. So if you increase the temperature, the ions can move faster and the conduction will increase. Okay, so these are the 5 factors that you should remember. Which of the following statements about the solutions of electrolytes is not correct? Okay, conductivity of the solution depends on the size of the ions. Yes, we discussed. Conductivity depends on the viscosity of the solution. Yes. Conductivity does not depend upon the solvation of ions present in the solution. Conductivity of the solutions increases with the temperature. These all factors are there if you talk about the third one. Okay. Solvation, it depends. If the ion is very small and it is solvated, then as a result it becomes very big and the mobility decreases. Okay, so conductivity of the solvation of ions is an important factor which determines the conductivity of the electrolytic solution. Okay. Okay, next let's understand some important terms and their definitions before going to discuss about it more. What is the first thing? Resistance. Resistance is something which opposes the flow of current. Okay, it is denoted by symbol R and the units are ohm. Next is resistivity. So resistivity means, suppose you have taken a wire or something, you have taken a wire whose length is 1 meter, cross sectional area is 1 meter square or 1 centimeter square. That particular rod experience how much resistance, that is called as resistivity. Okay, the resistance for a substance is its resistivity for a substance is its resistance when it is 1 meter long and its area is 1 meter square. Okay, so that is your rho and it is denoted by ohm meter or ohm centimeter. Next, conductance is just the inverse of resistance. Okay, so it is denoted by G and it is ohm inverse, or ohm inverse is called as S, Siemens. Similarly, conductivity, kappa, it is the inverse of resistivity. Okay, and conductivity by the electrolyte per unit volume. So if you have an electrolyte per unit volume, how much conductivity is there? Okay, suppose you have taken 5 liters of electrolyte, NaCl solution. It has conducted some amount of electricity. How much electricity is consumed per unit in 1 unit of volume? That is the conductivity of that particular electrolyte. Then it is its unit is as centimeter inverse, as meter inverse, ohm inverse, meter inverse, or ohm inverse, centimeter inverse. Then cell constant, we is represented it by Z star. Okay, and it is L by A. The formula of this one is L by A. Okay, length by area, units is centimeter inverse or meter inverse. Then you have molar conductance, it is represented by lambda m, and lambda m, that is your conductance of all the ions produced by 1 mole of an electrolyte in a specific volume of the solution. So suppose you have taken 5 moles or we have taken one electrolyte 5 molar. Okay, that means there are 5 moles of electrolyte. They have conducted a certain amount of electricity. 1 mole, how much it will conduct? That is your molar conductivity. Clear? These are the important terms that you should remember. Next, we'll go to formula. Resistance is equal to R into rho L by A. Rho is what? Resistivity. L by A is cell constant. Resistivity, rho, just I can reverse R A by L. Okay. Next, cell constant is represented by G star and this term is called as cell constant. Next, you have conductance. Conductance is the inverse of resistance. So I can write G is equal to 1 by R. Then you have conductivity, opposite of resistivity. So you can write it as like this. I will just reverse it. So it will become 1 by R into L by A. Okay, just the opposite of this one. Next, you have molar conductivity. Molar conductivity formula is lambda m is equal to kappa into 1000 by C. Here a condition that you should remember is that this K or the kappa should be in the unit of S centimeter inverse. Okay, then we have this formula. Clear? Now here is the question, which of the solutions has the highest conductivity? So we have discussed so many factors regarding conductivity, right? The solvent, solution, concentration, so many things are there. So concentration is almost same for all. Okay. Now type of electrolyte. You know, this is a weak electrolyte because it will not undergo complete dissociation, right? So this we can eliminate. Now these all three are strong electrolyte. Next thing, that factor which can affect is the size of the ions. Smaller the size of the ions, more is the conductivity. So here you can see we have Cl, Cl and NO3. Okay, these all are big ions. Here if you see Na plus, K plus and H plus. H plus is the ion which is very small, right? So that means this can conduct better. So the correct answer will be option number D here. Next we have the conductivity of a saturated solution of BaSO4 is given to you. Conductivity means kappa value is given to me for BaSO4, that is 3.06 into 10 to the power of minus 6. And its molar conductivity is also given, that is 1.53 S centimeter square mole inverse. Okay. Okay, next we have to find is KSP. So first of all, we can find that lambda m is equal to kappa into 1000 by C. Okay, so what is the value of kappa? It is 3.06 into 10 to the power of minus 6 into 10 to the power of 3 divided by C. C is how much? We have to find. Okay, and this one is 1.53. Okay, so if I just calculate, I will get 3.06 into 10 to the power of minus 6 into 10 to the power of minus 3 by 1.53. Okay, so it is 2 times, right? So 2 into 10 to the power of, sorry, this is plus 3, minus 3, so C square. So this C I can get is 2 into 10 to the power of minus 3. Now if you see what is the KSP for barium sulfate, it is Ba2 plus, okay, and SO4 2 minus. So it will be S square, right? So that is square of this one, 4 into 10 to the power of minus 6. Okay. Next, the molar conductivity is maximum for the solution of concentration. So we have this formula, right? Molar conductivity is equal to kappa by C. If C is less, molar conductivity will be higher. So it will be least in this one, so highest will be in this one, option number B here. Next, okay, variation of K and lambda m with concentration. This is very, very important. So first of all, talking about the molar conductivity. So remember, molar conductivity is what? The amount of electricity conducted by 1 mole of an electrolyte. Okay, so or it is concentration. Okay, so if you see lambda m, okay, is equal to kappa into 1000 by C, right? So if C is, or if you dilute the solution, okay, if the concentration decreases, then molar conductivity will increase, right? So the molar conductivity increases with the decrease in concentration for both strong and weak electrolyte. Okay, whether it is a strong electrolyte or weak electrolyte, if you dilute the electrolyte, the molar conductivity will definitely increase. Okay, this is because the total volume V of the solution containing 1 mole of electrolyte also increases. So if you see, this concentration formula is what? Number of moles by volume, right? Now if I increase the dilute it, if I increase, or if I add more water, or if I dilute it, then what? This V will increase. If V will increase, molar conductivity will increase. Okay, next thing we have, talking about K, kappa value. Okay, so kappa value is what? Conductivity per unit of volume. Okay, so if you see here, in case of this one, conductivity always decreases with the decrease in concentration, both for weak and strong electrolyte. Okay, so when you have more volume, the number of ions will be dispersed, right? So the number of ions per unit volume will decrease. That is why the conductivity per unit volume will also decrease. This can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases with the dilution. Okay, so you have to remember, if I decrease the concentration, okay, decrease the concentration, what will happen? Sorry, let me write it in simple words. If I decrease the concentration, molar conductivity will increase, kappa will decrease. Okay, this you have to remember. Okay, next, coming to molar conductivity, I said it will increase, but where it will increase? In case of weak electrolytes, the increase will be more. In case of strong electrolytes, there will be increase, but that will be less observable. So lambda m for weak electrolytes increases more due to the increase in dissociation of ions. So when you dilute the solution, the number of ions, the dissociation will increase, more ions will be created, so that is why the molar conductivity will increase. In case of strong electrolytes, what happens? Lambda m for strong electrolytes increases less due to the increase in the mobility of ions only. So earlier what happens? The ions were very close to each other, plus minus ions were close, so they used to attract contact each other. So their mobility was slow. When you have added a lot of amount of water, the Na plus and the Cl minus ions, or the positive and the negative ions, are now separated and can move independently. Their mobility increases. So that is why molar conductivity for strong electrolytes also increases, for weak electrolytes also increases. Here it increases due to the increase in dissociation, here it increases due to the increase in mobility. That is why here the increase will be more, here the increase will be less. Okay, so you can see that in the form of a graph. Okay, so suppose I'll explain this graph to you. See, KCl, right? When the concentration was almost like at 0.3, let me just assume this is 0.3. So the conductivity was up at this value. Now when you have decreased the concentration, okay, at this value, the conductivity has decreased. So how much increase is there? This much increase is there. Now if I talk about acetic acid, when the concentration was 0.4, okay, so the molar conductivity was this much. When it came here, you can see the increase in the molar conductivity, what range it has increased, right? So that is what we are saying. In case of weak electrolyte, the increase will be very much as compared to a strong electrolyte. Okay, now this graph is designed in the form of an equation that is called as your d by Huckel equation. Lambda m is equal to lambda naught m minus a delta c. Okay, A is same for the same type of electrolytes. Same type of electrolytes means, suppose I have one electrolyte NaCl and KBr. Okay, here I have +1, here I have -1, right? And here I have +1 and here I have -1. So these two types are called as 1,1 type electrolyte. Okay, if I have, for example, MgCl2, okay, and BeBr2. So here Mg is +2, chlorine is -1. So it is 2,1 type, and this is also 2, this is also -1, this is also 2,1 type. So that means when you have the two electrolytes whose cations are having same charge, anions are having same charge, they are called as same electrolytes or same type of electrolytes. And for the same type of electrolytes, this A value will be same. This has been asked in the previous year question, so please remember this one. Okay. So here's a question here, the pair of electrolytes that possess the same value for the d by Huckel constant in this equation. So here if I see, this is +1, this is +1, this is -1, this is -1. So they are of 1,1 type. Here if I see, this is +1, this is -1, this is +2, this is -2. So this is 1,1 type and the other one is 2,2 type. Now here I have +1, -1, here I have +2 and -1. So I can say this is 1,1 type and this is 2,1 type. Here I have +2, -2, here I have +1, here I have -2. So this is 2,2 type and this is 1,2 type. So now what I can see here is, you can see here only I am getting they are same type, so their A value will be same. So A is the correct answer. Okay. Next, coming to Kohlrausch's law. So now if you see the graph that I have shown you, just now we have discussed this graph, right? For strong weak electrolyte it was like this, for strong electrolyte it was like this. So at infinite dilution, means at like maximum dilution if you have done, at that point what will be the conductivity? So you can easily extrapolate this graph and find this value. But in case of weak electrolyte, what will happen? It will go like this, it will never touch this value. Right? So it is not easy, or we cannot calculate the molar conductivity of weak electrolytes at infinite dilution. Okay, so for that reason there is something, a law was discovered, or a law was given to calculate the molar conductivity of weak electrolytes at infinite dilution. Okay, and that law was your Kohlrausch's law. So what does this Kohlrausch's law tells you about limiting molar conductivity? What is limiting molar conductivity? When the concentration approaches 0, the molar conductivity is known as limiting molar conductivity. Okay, when the solution is too diluted, at that time whatever conductivity or the molar conductivity of that electrolyte is there, that is called as limiting molar conductivity, and it is denoted by lambda naught m. Okay. Okay, now I told you what is Kohlrausch's law. So Kohlrausch's law tells us that the limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the ions and cations of the electrolyte. So if I have like, one second, yes, suppose I have an electrode like this, AX and BY. So it has how many, or let me take a number for easy calculation. If I have A2, B3, okay, so I have 2A plus and 3B minus. So the total conductivity, okay, will be equal to 2 times the conductivity of A plus and 3 times the conductivity of B minus, right? So that is what is the molar conductivity of an electrolyte. Clear? This is given by Kohlrausch's law. Fine. Now let us see the applications of Kohlrausch's law. So it is used to calculate the alpha. What is alpha? The degree of dissociation of a weak electrolyte. What is alpha? Degree of dissociation of weak electrolyte. Okay, so it is lambda m by lambda naught m. Lambda m by lambda naught m. How to calculate this lambda m? This lambda naught m is calculated using Kohlrausch's law. So that is the indirect application. Okay. Next we have, if I substitute Ka, C alpha square by 1 minus alpha, and in term of alpha I will put this value, I will get this one. Okay, so after getting this one, you can calculate the dissociation constant of a weak acid. Next is to calculate the lambda m for weak electrolytes. This application we can understand by solving a question. I will explain you. Okay. So yes, this is the thing. Lambda m for NaCl is given to you. See, lambda naught of NaCl is how much? That this means it is equal to lambda naught of Na plus and lambda naught of Cl minus, which is equal to 126.4. Okay. Next we have HCl. So I have lambda naught of HCl, which is equal to lambda naught of H plus plus lambda naught of Cl minus, which is equal to 425.9. Okay. Next I have lambda naught of NaAC, okay, which is equal to lambda naught of Na plus lambda naught of AC minus, which is equal to 91.0. Okay. Now what I want to calculate lambda naught of HAC. Okay. So here you see this is a weak electrolyte. Okay. So this is equal to what? Lambda naught of H plus and lambda naught of AC minus. So you have to find where I will get H plus out of these equations. I will get in this equation, right? So I have to take this one. So if I take this one, that is lambda of HCl. Then where I will get AC? In the fourth one, that is lambda naught of NaAC. Now if you add these two, you will get H plus and AC minus, but you will also get an extra NaCl. So to cancel that, I will take minus of NaCl. Okay. So if I add this one, I will get 425.9, okay, plus 91.0, okay. After that, I will subtract minus 126.4. Okay, so let us calculate this one. 425.9, okay, plus 91.0, that will give me 516, right? Now 516 minus 126.4, okay, so this will give me 390.5, that is my option number D here. Okay, that is the application of Kohlrausch's law. Specific conductance of 0.1 molar HNO3 is given. The molar conductance of the solution is, so specific conductance is same as your kappa value. Okay, so lambda K value is given to me, which is 6.3 into 10 to the power of minus 2. Okay, next I have S centimeter inverse. Okay, concentration value is also given to me, that is my concentration is 0.1 molar. Okay. Now I want to calculate the molar conductivity, which is equal to kappa into 1000 by C. So kappa value is 6.3 into 10 to the power of minus 2, 1000 is 10 to the power of 3, and C is 10 to the power of minus 1. Okay. So now if I go, this goes up, okay, it will become plus 4. So 6.3 into 10 to the power of 2, okay, or I can write 630. Yes, so this one will be the answer here, 630. Okay. Now I have a question, one more thing. Not a question, I want to tell you one more formula. If kappa is in S meter inverse, okay, then the formula for lambda m is kappa by C into 1000, okay, where kappa should be in the unit of S meter inverse. So please remember, if it is in centimeter inverse, then it is kappa into 1000 by C. If it is in meter inverse, then kappa into 1000, kappa by C into 1000. Okay. Fine. Next, at a particular temperature, the ratio of molar conductance to specific conductance of 0.01 m NaCl is. So if you have this one, lambda m is equal to kappa into 1000 by C. You want to calculate the ratio of molar conductance to specific conductance, means lambda m by kappa. Okay, 1000 by C. C is how much? 10 to the power of minus 2. Okay, so this is 10 to the power of 3 minus 2, it will become 10 to the power of 5. So option number A. Okay, why I am taking C? Because by options you can see it is in centimeter, so I have taken this formula. Next, we can see just all the formulas quickly, okay, so that all of you have remembered whatever we discussed. So yes, Faraday's first law, M is equal to ZIT. Second law, M1 by M2 is equal to E1 by E2. Resistance R is equal to rho into L by A. Resistivity rho is R A by L. Cell constant G star L by A. Conductance G 1 by R. Conductivity 1 by R dot L by A. Molar conductivity is kappa into 1000 by C. Okay. Next, we'll go to third part where we are going to discuss about, one second. Okay. Next, third part is battery. This is mostly the theoretical part. Okay, not much reactions are there. So batteries are of two types: primary batteries and secondary batteries. Okay, primary batteries are those which cannot be recharged. It is one-time use. Secondary batteries are those which can be recharged. Okay. Then we'll discuss what is fuel cell, hydrogen oxygen fuel cell. Yes. Then we have here corrosion. We'll talk about the corrosion, why it is a redox reaction and what reaction takes place here. So quickly coming to batteries, so as I told you, primary batteries and secondary batteries. So here we have just a minute. Yes, primary batteries are those which can, where the reaction occurs only once. Okay, it can be used only once, cannot be reused. Examples are your dry cell and mercury cell. Okay, whereas secondary batteries are those which can be recharged by passing current through it in the opposite direction, so that it can be used again. Here examples are your lead battery and nickel cadmium battery. Okay, let us quickly see the first one. So you have to just remember what is the anode, what is the cathode in each of them. Okay, so here anode is zinc, cathode is MnO2. In mercury cell, anode is zinc and cathode is mercury. Okay, so reactions you don't have to remember. Clear? Next, if you go to lead storage, yes, for lead battery you should remember the reactions. So in the lead storage cell, what happens in the anode reaction, lead gets oxidized to lead oxide, lead sulfate, okay, Pb to Pb plus 2. And in the cathode part, what happens, PbO2 gets reduced to PbSO4. So lead reactions you should remember. Okay, at anode what happens, lead oxidized to lead sulfate, at cathode lead oxide reduced to lead sulfate. So this reaction is happening when the battery is used. When you recharge the battery, because these are secondary batteries, right, when you recharge the batteries, the reaction reverses. Reverses means what happens here at anode, PbSO4 gets converted to Pb, okay, and here PbSO4 gets converted to PbO2. Okay, that is the reaction that happens during the recharging process. Okay, I have a question on this, I will be explaining you that. Next, nickel cadmium, cadmium is the anode and nickel is the cathode. Okay. Okay, next you can see the reactions for nickel cadmium cell, the complete reaction, but this is not essential. This is what something you must remember, very very important. So you can see lead to lead sulfide during the oxidation, lead oxide to lead sulfate, this is the reduction, anode reaction and cathode reaction. Okay, next we have fuel cell. Fuel cells are what? So these are the cells where the energy is produced due to the combustion reaction. Okay, so galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called as fuel cells. So these are a type of galvanic cell, okay, where the combustion reaction takes place and the combustion reaction is converted to electrical energy. Okay, so one of the most successful fuel cells was your hydrogen with oxygen to form water. In the cell, hydrogen and oxygen are bubbled through the porous carbon electrodes into the concentrated aqueous NaOH solution. Catalyst used here, you should remember, finely divided platinum or palladium. Okay, then we have here, yes, so at cathode what happens, oxidation is there, it gains 4 electrons and get converted to 4 OH minus. So this is your reduction reaction. Anode is here, that is where loss of electrons is taking place. Hydrogen is getting converted to water. Now if you add these two reactions, we will have H2 plus O2 gives you H2O. So please remember, at anode there is oxidation of H2 and at cathode there is reduction of O2. Okay, fine. Next we'll talk about the corrosion. So here you can see the corrosion, whichever spot the metal is getting oxidized, right? Suppose here iron is there, it is getting oxidized and it releases Fe2 plus electrons. These Fe electrons move to another site from where in the presence of H plus and O2 water produced, okay, and this one is getting reduced there. Okay, so now you can see here, from here O2 is there, Fe2 plus has been produced and FeO2 gives you Fe2O3, which is finally the rust. You can check here, oxidation first, Fe undergoes oxidation, then O2 present in the atmosphere with the H plus that is present again in the atmosphere takes these electrons and gets converted to H2O. Now what happens, this Fe2 plus and this H2O and some amount of oxygen combines to give you oxides of iron, which is nothing but rust. Okay, fine. So next we'll see some PYQs here. A secondary cell is one in which, very simple question, it can be recharged by passing the current in the opposite direction, not in the same direction, in the opposite direction. Next, while charging the lead storage battery, okay, this question I want to discuss in detail. So now you see, at anode what happens, Pb gets converted to PbSO4, right? This is your oxidation reaction. And at cathode what happens, PbO2 gets converted to PbSO4, reduction, right? Now you can see here it is 0 and this is plus 2, this is 0 plus 4 and this is plus 2. Now once you recharge the battery, okay, the reaction is reversed, means this reaction takes place here and this reaction takes place here. So at anode what is happening now, reduction, and at cathode what is happening here, oxidation, right? So I can say that the first statement, see, PbSO4 on cathode, so you have to tell during recharging, okay, so means the opposite reactions. PbSO4 on cathode is reduced, no, PbSO4 on cathode is undergoing oxidation, so this is wrong. PbSO4 on anode is undergoing oxidation, no. PbSO4 on anode is reduced, yes, PbSO4 on anode is reduced to Pb. That is the correct answer, option number C here. Okay. Okay, so that's all students. In this one short video I have given you all the important formulas, concepts, questions, everything is done. So I hope this video would be helpful for you for a quick revision during the KCET examination. And yes, if you have any doubt in these videos, please put down in the comment section. I will definitely address it. Thank you for watching and do not forget to subscribe the channel.